Now, it's a great pleasure and honor to introduce Moshe Vardi as the speaker of this first Logic at Large lecture. Moshe is a university professor and distinguished service professor in computational engineering at Rice University in Houston, Texas. And he is arguably the most influential theoretical computer scientist today, having made groundbreaking contributions in a wide variety of topics at the interface of logic and computer science, including program verification, database theory, finite model theory, and reasoning about knowledge. Now, in addition to his research, his service to the theoretical computer science community is unparalleled. It's impossible to mention everything, but for example, he's a founding editor of the open access journal Logical Methods in Computer Science, the co-founder of the conference series TARC, Theoretical Aspects of Reasoning About Knowledge. He's the general chair of the steering committee of FLOC, the Federated Logic Conference, since its beginning in 1996, and a senior editor and formerly editor-in-chief for a decade of the communications of the ACM. Now, he holds numerous distinctions, fellowships, and memberships of academies, again, too many to list here. But in the past week, this list has been extended even further as Moshe received the highly prestigious Donald D. Knuth Prize for high impact seminal contributions to the foundations of computer science, and also the ACM AAAI Alan Newell Award for contributions to the development of logic as a unifying foundational framework and a tool for modeling computational systems. And in addition, he yesterday gave the Gödel lecture in Vienna. So being in such high demand, we are very thankful to Moshe for accepting our invitation to speak here today. So please, I give the word to Moshe Vardi.
Okay, can you hear me now? Yes, okay. Thank you very much for the very kind introduction. It's been a pretty amazing week, I must say. Not every week is like this, especially in this, what I consider very bleak times. It's nice to have some good news. So I would like to offer you today, and I'm very happy to give this lecture for the outreach lecture for the VvL. And I was happy to learn about VvL more than I know, much more than I knew before. So what I'd like to try to offer today is a vision from 50,000 feet of this, to me, absolutely amazing connection between logic and computer science. Now I should be able to, okay, I can scroll. And it is an amazing connection because if you think of logic, you know, we go back to Aristotle, you can think of it as almost the oldest intellectual discipline. And computer science is maybe perhaps the youngest intellectual discipline. So this is a pretty amazing connection. And I think that when I did research for this topic, I found someone at the Santa Fe Institute, Cosmo Arshalizi, who also expressed his wonder about this connection. And he wrote, if in 1901, a talented and sympathetic outsider had been called upon, say by a grant-given agency, to survey the sciences and name the branch that would be the least fruitful in the century ahead, his choice might well have settled upon mathematical logic, an exceedingly recognized field whose practitioner could all fit in a small auditorium, and no practical application, not even that much mathematics to show for itself. Its crown was an extremely obscure definition of cardinal numbers, whatever they are. But before we go deeper into try to explain the connection between logic and computing, we need to understand what is logic. It is actually not so easy to define logic. And we may want to go to probably, I think, the most famous logician. It's not the most famous logician is not Aristotle. It is the Reverend Charles Ludwig Dodson, also known as Lewis Carroll. And he has a definition of logic in Ali Through the Looking Glass. Contrariwise, continued Tweedledee, if it was so, it might be. If it were so, it would be. But as it isn't, it ain't. That's logic. And if you're unsatisfied with the 19th century definition, you may jump and find a 20th century definition by Andrea Nye, a feminist writer. Logic is the creation of defensive male subjects who have lost touch with their lived experience and define all being in rigid propositional categories modeled on a primal contrast between male and female. But enough joking. If you want a serious definition, we'll have to go to the very beginning of logic. We have to go to Aristotle in the 4th century BC. And the Greek loved debating, and the question was, what is a solid argument? And the question wanted to know what would distinguish philosophy, which is love of wisdom, from demagoguery. Demagogue means leader of the people, literally. Demagogue means leader of the people. And I like the definition of Francis Bacon from almost 2,000 years later. Logic differs from rhetoric in this, that logic handles reason, exact, and in truth. And rhetoric handles it as it planted in popular opinions and manners. So when I start my class on logic and computer science, I tell the students, what is logic? Logic is the search for truth. There could be nothing more fundamental intellectually than searching for the truth. So Aristotle made to me an astounding discovery. So you look at the syllogism, and the most famous one is all humans are, syllogism means forms of reasoning. All humans are mortal, all Greeks are human, therefore all Greeks are mortal, and we recognize it as valid reasoning. You ask people, they'll say, yes, it does follow. But here is another one. All Bujums are Slizy, all Tovs are Bujums, therefore all Tovs are Slizy. And here I'm using this nonsense poem, Jabberwocky, from Alice Cole to borrow some words. And of course, you have never seen a Tov, you don't know what is a Bujum, and you have no idea why they are Slizy. But the argument is as solid as it was when we talked about mortals and Greeks and humans. So truth come out of form, and that's an amazing observation, because we typically think that the forms is inessential, right? It's the inner thing that matters. But we see that part of the search for the truth is to look at the form. Now, the Greeks, a bit later, also discovered the paradox. The paradoxes were a wonderful tool to sharpen your mind. And there are many paradoxes. The most famous one is the liar's paradox, which will play a major role here. It's attributed to Epimenides, who said all Cretans are liars. And in fact, we find in the epistle of St. Paul to Titus 1:12, one of themselves, a prophet of their own, said Cretans are always liars, evil beasts, lazy gluttons. I guess they're really not very popular. In fact, the psalmist was a bit, in Psalm 116:11, we found everyone is a liar. But if you really want to get the sharp paradox is due to Euclid, who said this sentence is false. And I just recently discovered there is a very nice Star Trek episode where they defeat one of this some kind of a robot by giving him the liar's paradox, and you see literally the robot's head burning out of this paradox. So it's really fun to play with this paradox with children, because you can almost track their mental development by the time to see when do they understand the difficulty of this paradox. So it's fun. And the key feature here is self-referent. The sentence talk about itself. We will see this is an important feature. I'm going to jump over the Stoics, who made contribution to propositional logic, and I'm going to jump to the Middle Ages, and we're going to visit a Catalan monk, Ramon Llull, who was quite a sinner as a young man, but then he had an epiphany and became very devout, and he wanted to use logic to convert the whole world to Christianity. And in his book, you find argument in favor of the Trinity, a very compelling argument. If in thy three properties there were no differences, demonstration would give the D to the H of the H with the F and the G as it does with the E. And the K would not give significance to the H of any defect in the F or the G. And since diversity shown in the demonstration that the D makes of the E and the F and the G with the I and the K, therefore the H has certain scientific knowledge of thy holy and glorious Trinity. Convinced? Well, if you're not convinced, if you're at least skeptical, you're not the only one. We can go back to Francis Bacon, who says some person more ostentatious and learned have labored about a kind of a method not worthy to be called a legitimate method, begging rather a method of imposture, which nevertheless would no doubt be very acceptable to meddling wits. Such was the art of Llull. So clearly he don't think of much of the art of Llull. In fact, Llull went to North Africa to convert the Muslim to Christianity, and they were so unhappy with his logical argument that he was stoned to death. He was in his 80s, and he was stoned to death in North Africa. But perhaps we should not be dismissing Llull so easily, because really that symbol is a standard. Today we use it all the time. We name propositions by letters to give them a name, symbolic name that is easy to manipulate. And Lull realized that as you do reasoning, you need to deal with, you have case explosion. You have to deal with many combination. And it's hard to keep track of all these combination. So now here you can see, this is from his book. The title is wonderful, Ars Magna Generalis and Ultima. This could be the title of your next book, right? Great General and Ultimate Art. That's a nice title for a book. But you see that the letters stand for, like, B is for Bonitas, which I think is good, and K is Gloria, and etc., etc. But this was circle that you can rotate. By rotating the circle, you create different kind of combinations. And what's important about it, that this is mechanical aid to reasoning. And as far as we know, this is the first time that someone will propose mechanical aid to reasoning. Of course, mechanical aid to computation are much older. Abacai has a much older history. But as far as we know, Lull was the first one that said reasoning also requires some kind of computational effort, and we need to use some aids, mechanical aids. And even though Francis Bacon dismissed it, Leibniz, the man who brought us calculus, but also he is the inventor of the bits, binary notation. So one of the patron saints of computing, you can say. He beat calculator. He was very much inspired by Lull. Now, Leibniz was a prodigy. He taught himself Latin at age 8. He read Aristotle. He wrote a thesis at age 20 about Aristotelian metaphysics, and another one on logic in the law. And he discovered Lull. And he wrote later, when I was young, I found pleasure in the Lullian art. And out of this primitive idea of rotating circles, Leibniz came up with absolutely amazing visionary idea of a universal mathematical language, which he called lingua characteristica universalis, in which all human knowledge can be expressed. And calculational rules, reasoning calculus, calculus ratiocinator, carried out by machine to derive logical relationships. And he wrote, if controversies were to arise, there would be no more need of disputation between two philosophers than between two accountants, for which suffice to take their pencil in their hands and say to each other, calculemos, let us calculate. So Leibniz, again, as far as you know, is the first person who argued that reasoning can be mechanized. Now, Leibniz did not get to carry out his dream very far. Unlike his nemesis Newton, who was a professor at Cambridge, Leibniz was a librarian for the Duke of Braunschweig, and he did all of his philosophy and science and mathematics on the side, so to speak. Much of what he wrote, and he wrote voluminously, was not really published until the 20th century. So there is a huge gap between our view of Leibniz today and when Leibniz was alive. In fact, I think that what I read is when he died, only his secretary attended his funeral. He was actually a lonely man. But 150 years later, his work on reasoning calculus was followed by a man who is described as of acutest intellect and manifold learning, George Boole. George Boole is born in Victorian England. His father is a shoemaker. You might reason that in Victorian England, if your father is a shoemaker, you are very likely to grow up and become a shoemaker. But he was incredibly bright even as a boy. His father got into a huge argument with the school principal because Boole translated an ode by Horace from Latin to English, and translation was so beautiful that the principal could not believe that this was done by a young teenage boy. And he ended up with no formal education beyond elementary school. He ended up being a professor of mathematics in King's College in Cork, Ireland. And you have to remember, the 19th century is a century of the development of abstract algebra. And Boole had this amazing insight that logic, the syllogism, are about classes of objects. When we talk about mortal, about human, these are all classes of objects, sets. Today we would say sets. And you can manipulate them algebraically. And so what today we think of Boolean algebra is the insight of Boole that conjunction can be viewed as a product operation. And disjunction can be viewed as an addition operation. Now remember, we talked about mechanizing calculus, mechanizing reasoning, calculus ratiocinator. Indeed, in the introduction to his book from 1847, The Mathematical Analysis of Logic, Boole wrote, "The design of the following treatise is to investigate the fundamental laws of the operations of the mind by which reasoning is performed, to give expression to them in a symbolic language of calculus, and upon this foundation to establish the science of logic and construct its method." From his point of view, he was writing a book in cognitive science. How does the brain work? Now, today, of course, we understand, we know a little better, and yes, we reason logically sometimes, but it's much more complicated than that. But nevertheless, Boole was formalizing the operations of the mind, and he did it algebraically. And what he showed is that out of this algebraic approach, you get philosophical insights. For example, he said conjunction should be idempotent. White is the same as white and white. So x equal x times x. And now you lead the little algebraic manipulation, and you get that x times 1 minus x is 0. And he said, oh, this is the principle of contradiction, that something cannot be true and false in the same time. You cannot be in the class and not in the class at the same time. And this is, he said, the principle of contradiction, which Aristotle established as the most fundamental axiom of all philosophy. So we can argue about the excluded middle, but something cannot be both white and not white at the same time. That over this, there should be no debate. This is the most fundamental axiom of all of philosophy. Now, Boole also did not get to carry his life work too much. He died. You can see he died. He was fairly young when he died. He was about just in his 40s when he dies, 50s, early 50s when he died. And he got pneumonia, and he died young. But his work was continued by his follower, William Stanley Jevons. In fact, what we call Boolean algebra really should be called Jevonsian algebra, because Boole, when he used disjunction, used exclusive OR. And it was Jevons who argued in favor. He said the inclusive OR give us nicer algebra. And he named the algebra after Boole in Boole's honor. So Boole's algebra does not mean that Boole invented this algebra, but it was named after Boole. And it's amazing to read what Jevons thinks about logic. So one is Jevons build logic tools. This is the first, as we know, logic machine. This is a machine that can reason. It can reason about 4 Boolean propositions by means of moving wooden pieces. So don't laugh at it if you think, if you can build it, good for you. It's not so simple. And it's just, I want to put a few quotes from Jevons. I have given much attention, therefore, to lessening both the manual and mental labor of the process. And I shall describe several devices which may be adopted for saving travel and risk of mistake. What is the process? The process is logical reasoning. Okay. And we will, so already in the 19th century, people are aware that logical reasoning is very difficult. And we will see later on in 20th century, what is the mathematical meaning of this difficulty. The next what I love, and I always read it to my graduate students, I said, this is how excited you should be, is I awoke in the morning, the sun was shining brightly into my room. There was a consciousness on my mind that I was the discoverer of the new true logic of the future. For a few minutes, I felt such a delight, such as one can seldom hope to feel. This is how we should all feel about our research, this kind of an excitement. Now, the other interesting thing is he's thinking about computing. He said the machine represents a mind endowed with powers of thoughts, but wholly devoid of knowledge. It cannot be asserted indeed that the machine entirely supersedes the agency of conscious thoughts. So this is some very much part of what we are discussing today about AI. And you can see that in the 19th century, Jevons being the machine that can handle 4 propositions, and is already thinking about what is the meaning of intelligence, of knowledge. The last remark is, of course, very ironic. It goes on with the same story about after the discovery of the electron, there was a toast in a party to the electron, which will never be of any use to anyone. So here, Jevons writes, I must remark that these mechanical devices are not likely to possess much practical utility. We do not require in common life to be constantly solving complex logical questions. So he thought this was a nice but not very practical device. But my argument is that we go from the logical piano, we go to the iPhone, which is of immense practical significance. And how did this transition that if you can do logic, it's related to computing? I have yet to explain it. We saw some intimation with Lull and with Leibniz, but how did this development actually happen? Now, some people attributed an important step to Claude Elwood Shannon. So Shannon, of course, is most famous for information theory, which underlined much of modern communication. But he did information theory when he was quite old, when he was 28. What did he do when he was still young? So at age 21, Shannon writes a master thesis. And the master thesis is about the connection between logic and switching circuits. Because what he realized that if you remember, you learn a little bit about circuits in physics and electricity, you can connect circuits in series, and that corresponds to a conjunction, or in parallel, and that corresponds to a disjunction. And he realized also a switch can be open, which is 0, or closed, which is 1. And he realized that if you want to describe circuits, combinational circuits, as we call them, you can do it using Boolean logic. And this was a master thesis. Today, you can find it on the web. Herman Goldstein, who was the ENIAC project manager, we're going to see the ENIAC a little later, wrote this thesis helped to change its circuit design from art to science, because now you have a mathematical formalism to describe circuits. Howard Gardner, a professor at Harvard, wrote possibly the most important, the most famous master thesis of the century. But it turns out that this is a bit of exaggeration. So somebody wrote a master thesis in 1937. It wasn't on the web. It wasn't widely published. It was not widely circulated. So the people who build, remember the year in 1937, already in this time, you have in the United States, Atanasov, and in Germany, Zeus, building computers. And they said they knew nothing about Shannon's work. In fact, from a book on digital circuit design from 1971, in introduction, the author R.K. Richards said Boolean algebra was something less than a major influence in the invention and design of early electronic computers. The 1950s were well underway before the algebra was used at all as some of the major pioneering electronic computing organizations. On the other side, it turns out that other people have discovered this connection independently of Shannon. There have been written documents that even though they have never published it, Max Newman and the people in Bletchley Park, they developed the Colossus, they used it. In fact, we find paper for 1941, 1936 independently, but even 1910, Paul Ehrenfest, 1910, made a connection between switching algebra and switching circuits and logical algebra. And perhaps I think the connection even goes back all the way to the 19th century, where we meet a figure of mysterious greatness, Charles Saunders Peirce. Charles Saunders Peirce was a mathematician, an astronomer, a chemist, geodesist, surveyor, cartographer, meteorologist, spectroscopist, engineer, inventor, psychologist, philologist, lexicographer, historian of science, mathematical economist, lifelong student of medicine, book reviewer, dramatist, actor, short story writer, phenomenologist, semiotician, logician, rhetorician, metaphysician, all of this in his spare time, of course. So we can spend, you can see, we can spend a whole hour just talking about Charles Saunders Peirce, but I will jump immediately to his student. In 1887, Alain Marquand, his student, published an article in the Proceedings of the American Academy of Arts and Science called A New Logical Machine, which was a follow-up work on Givon's work. The article caused quite an excitement. Charles Kendall Adam, who was the president of Cornell, was excited. Dear sir, please accept my thanks for a new logical machine. Could you invent a machine that will do the work of a college president? I give you my order in advance. This is still being debated whether a machine can do the work of a college president. Peirce read the article and he liked it, but he wrote to Marquand, he said, it's time to build machines not for this easy logical problem, for very difficult mathematical problem. I think electricity would be the best thing to rely on, enough with these moving wooden pieces. And he actually he wrote circuits, how to do multiplication and addition in logic. So this connection, this understanding of, and Peirce was a logician. In fact, the introduction of, remember that all the syllogism were monadic logic. Peirce was one of the people that argued that developed calculus of relations, that we need to go to higher order relations for logical reasoning. He one of the inventor of the quantifiers. Now, when we talk again, so here is someone that just thought about that we can use logic to build computation. He was a philosopher. He was done. He did not build this machine. But for him, this was enough to write a logical machine is a machine which being fed with premises, produces the necessary conclusions from them. The value of logical machines seems to lie in their showing how far reasoning is a mechanical process. Calculating machines are specialized logical machines. So this is, as we know, I mean, remember, we saw Leibniz talk about reasoning calculus, but here Peirce says reasoning is mechanical and calculation is a special case of it. And he goes on to think, what are the consequences of this? Precisely how much the business of thinking a machine could be possibly made to perform, and what part of it must be left to the living mind is a question not without considerable practical importance. The study of it, in any rate, not fail to throw needed light on the nature of the reasoning process. When I take this quote and I show it to people, I say, who do you think wrote it? Some people say John McCarthy, some people say Alan Turing. It's just amazing to realize that this was written in 1887 by a philosopher. And again, some of the questions we ask today about AI, he writes, nobody has proven that automatic engine cannot exercise self-control beyond specific adjustment for which construction has provided. This is one of the questions we're still asking today. Are we going to build AI that will have agency? And very much still an open question. Now, when we talk about mathematical logic so far, you can take the term mathematical logic in two senses. One is let's treat logic mathematically. And this is something, for example, Boole has started. Boole has turned logic into mathematics, and that continues today to mathematical logic. It's a mathematical discipline. But the other thread of this is using logic to shed light on mathematics. And this will be the second half of this talk. And Eugene Wigner wrote a very famous, who went on to win the Nobel Prize in 1963, wrote a very famous article in 1960 on unreasonable effectiveness of mathematics in the natural sciences. And he started with he was based his article on even quotes from Euclid, who wrote the laws of nature about the mathematical thoughts of God, or Galileo, who wrote the universe cannot be read until we've learned the language and become familiar with the characters in which it is written. It is written in a mathematical language. And Wigner formulated what we call an empirical law of epistemology. It's empirical because it's so far that he's worked really well, that at least for the physical sciences, the biological sciences, it's more complicated. But in the physical sciences, the mathematical formulation of the laws of nature is both appropriate and accurate. Mathematics is the correct language formulating the laws of nature. And of course, this makes people ask all kinds of questions. For example, why is the case? Why is the universe behaving mathematically? But other question is, what made mathematics so reliable? When we think of mathematics, we use the term mathematical certainty, for example. We don't use it for any other discipline. We never say psychological certainty. There's no certainty in the social sciences. Mathematical certainty. What's special about mathematics? And the answer is mathematics have something very, very special. Proofs that we call the high road to truth. The legends are when the Greek discovered the deductive proof of Pythagoras' theorem, they thought this was a gift from the gods, and they slaughtered an ox to thank Apollo for this wonderful gift, the proof. And so to understand the importance, really, this early discovery in mathematics had, we have to go back to Euclid in the 4th and 3rd century BC, who is probably the most influential mathematician of all time, not the best mathematician. Archimedes is considered to be the best mathematician of all time. But Euclid wrote a textbook So we're still essentially elements, which is the textbook for plane geometry. And we all have learned in high school from essentially a version of Euclid's book. So until the 19th century, in fact, even in high school, if you think about the way you learn in high school, you learn deductive mathematics. It was in geometry. In fact, the whole purpose that today we learn plane geometry in high school is to teach us deductive reasoning. But then you go to algebra and calculus and you get recipes. You don't get the same kind of deductive reasoning there. And things are much more complicated. You know, they're indebatable. The Greeks had a very hard time with irrational numbers. And do they exist or not? And this relationship that the geometry is the queen of mathematics went until the 19th century, where we had a reversal. And part of the reversal was people discovered that there are other geometries. Plane geometry is just one geometry. And the other piece was that the calculus, which was a bunch of recipes, was finally formalized and became analysis. But when you look at this formalization, you run into limits, and limits are about the infinite, infinitely large, infinitely small. And that caused a question. People start asking, wait a minute, we assume that we all know what is a rigorous proof, that there is no debate about what is a rigorous proof. And now people start to question, are we all in agreement about what is a rigorous proof? And the most difficult part of this foundation of calculus is the infinite. And the infinite has been a mathematical controversy, again, going back to Aristotle. Aristotle did not believe in the infinite. He said infinitum actu non datur. There's no actual infinity. When infinitely, you can count larger and larger number, but I don't believe there are infinitely many numbers. Somehow he had a hard time with this infinite. And St. Augustine said, wait a minute. Yes, any human can only count finitely many numbers, but God sits above it all, and God sees the infinitude of the numbers. So what do you mean we don't have infinitely many numbers? There's a wonderful book about the infinite by Amir Axel called The Mystery of the Aleph. And this is from the introduction, first discovered by the Greeks between the 5th and the century BC. The Zeno paradoxes are really, it sounds a paradox about the infinite. The concept of infinity was so overwhelming, so bizarre, so contrary to every human intuition, that it confounded the ancient philosopher and mathematician who discovered it, causing pain, insanity, and at least one murder we know of, which is a whole other long story here. And from a philosophical controversy, it became a mathematical controversy when in 1874, Georg Cantor proved there are infinitely many different infinities. And of course, what does he use? The same old technique, diagonalization. Remember, we saw diagonalization. It's being used here to show there are infinitely many distinct infinities. So mathematicians have debated over the generations about the infinite. Leibniz loved it. I'm so in favor of the actual infinite, instead of admitting that nature abhors it, I hold that nature makes frequent use of it everywhere. Gauss hated it. I protest above all the use of infinite quantity as a completed one, which in mathematics is never allowed, verboten. Kronecker thought this was not mathematics. When he saw the proof of the Bolzano-Weierstrass theorem, he said, obvious sophism. Hilbert loved it. No one shall be able to expel us from the paradise that Cantor created for us. Some people still refer to set theory as the Cantorian paradise. And Frege wrote, for the infinite will eventually refuse to be excluded from arithmetics. Thus, we can foresee that this issue will provide for a momentous and decisive battle. And indeed, there was a battle, and this was the battle that I don't have time at all to talk about it. And this is the huge fight between Hilbert and Bauer. And that could be a whole topic of a whole other talk. And you have some people in the Netherlands are expert in the history of this battle. So let's go back to Frege. Frege, described by some, is the second most important logician after Aristotle. Why is that? What is a great contribution to logic? So in 1879, Frege wrote a small book called Begriffsschrift, a language for concept, in which he tried to answer the question. Again, this is some of the early work in philosophy of mathematics. What makes mathematics so reliable? And Frege asked, what is the language of mathematics? Does mathematics have a universal language? And the answer was yes. And this is really the foundation of what today we would call first order logic. He said, all mathematical discourses are about mathematical objects, relationships between them, function between them, logical operation. He is a follower of Boole, and quantifiers. Quantifiers have been discovered by Peirce, by Peano. We said that we use mathematics. We say all the time we use quantifiers. And it's the first time we can go back to Aristotelian syllogism, and now we can formalize it and realize it's really about the implication and quantifiers. Von Heyernoth, who wrote a famous anthology from Frege to Gödel in 1967, wrote perhaps the most important single work ever written in logic. I still think that Aristotle's book was maybe the most important work, but this could be at least number 2. Then get into the picture of British philosopher, Bernard Arthur William Russell, coming from kind of very British aristocracy. And here's a picture when he's probably in his 80s or even 90s. But in 1902, when he's about 30 years old, he writes a letter to Frege. And the letter is about Frege's book. And the letter starts very complimentary at the beginning. I find myself in agreement with you on all essentials. I find in your work, discussion, distinction, definition, that one seeks in vain in the work of other logicians. There's just one point where I've encountered the difficulty. And this one minor difficulty really was showing that Frege's system was inconsistent. And Frege was crushed. He was just about to publish another book. And the book has already gone to the publisher. So all he can do is add an appendix. And he said, there's nothing worse that can happen to a scientist than to have the foundation collapse just as the work is finished. I've been placed in this position by later Robinson Bernard Russell. So imagine you write a book, in the appendix you write, by the way, everything you've read so far, it's inconsistent. And for Frege, this was a shattering blow. He could never see how to overcome this contradiction. And towards the end of his life, he became an extremist, extreme right-winger. He hates the parliament, democracy, liberals, Catholic, French, and above all, he became a virulent anti-Semite. And this happened just before the rise of Nazism. So it was really a very tragic end of intellectually a very distinguished career. So what is this paradox? So this is a paradox. This is became known now as Russell's paradox. So again, Russell realized that the fundamental concept are classes of objects, sets. This is really what the foundation of mathematics is, talk about classes of objects. And Russell asked, what about the collection of all sets do not include themselves as members? Is this a set or not a set? And he showed that there is no simple definition of what is a set. And he gave a beautiful story about a barber in a small town, a man, he shaves all men and only those men who do not shave themselves. And then you can ask again, you can try with children, should this barber shave himself or not? And either case, you get a contradiction. And again, it's the last paradox. And Epimenides spoke from a grave after 2,500 years. But now we have a foundational crisis in mathematics, because if set theory is the most fundamental part of mathematics, and it has paradoxes, then we are in big trouble. And this foundational crisis, something that Russell himself wanted to address. And he embarked on a project that eventually was published at Principia Mathematica, which was incredibly demanding project. It was a 10-year work, and he wrote about it. Every morning, I would sit down before a blank sheet of paper. Throughout the day, with a brief interval for lunch is important, I would stare at the blank sheet. Often when evening came, it was still empty. It seemed quite likely that the whole of the rest of my life might be consumed in looking at that blank sheet of paper. So if you sometimes feel like you have a writer's block, you're not the only one. But Russell recruited Whitehead to help him, and they produced, after 10 years work, 3 volumes, 2,000 pages. And it was a systematic derivation from mathematics, from logic, avoiding the obvious paradoxes. They introduced types to disable the self-reference. And Russell himself, after that, wrote, my own intellect never quite recovered from the strain of writing it. I turned aside from mathematical logic with kind of nausea. So after that, he did no more logic. And at first, it seems, okay, he solved the problem. And then people realize, wait a minute. Frege had a small book, and Frege and Russell found a paradox. Now you have 2,000 pages. Who knows how many paradoxes are lurking in these 2,000 pages? So they said, no. A 2,000 page argument is not a satisfying solution to the foundational crisis. And into that crisis step David Hilbert, who at around the turn of the 20th century is the king of mathematics. And we don't have today people that are kind of have the stature of the top mathematician in the world. We'll see one more. But this was David Hilbert. Again, there are many legends about Hilbert. One of my favorite one is one of his students got sick and died. And at the funeral, Hilbert say, this is a huge loss. At the time of his death, Paul was working on a meromorphic function. Let me explain to you what he was working on. And he goes on to give a 45-minute beautiful mathematical discourse on his students' work. So Hilbert launched after World War I what became known later as Hilbert's program. And it ended up having 3 legs. The most important part for him was showing there are no paradoxes. So mathematics is consistent. You can prove something and its negation. But he became more ambitious. He wanted to show that mathematics is complete. You can answer all mathematical questions. And this is where you see computing is being born here again. Mathematics is decidable. There's a mechanical way to determine whether a given mathematical statement is true or false. So let's again go and find, I'll read you some quotes from Hilbert. So what was his goal? He wanted to dispose of the foundational questions once and for all. Every mathematical problem must necessarily be susceptible to an exact statement, either in the form of actual answer to the question asked, or by the proof of impossibility of its solution. So we have many negative answers in mathematics, right? You cannot trisect an angle but with a ruler and a compass. It's a negative result. You cannot square the circle. It's a negative result. And here is again where computing is starting to be born. Once a logical formalism is established, one can expect that the systematic, so to say, computational treatment of logic formula is possible, which would somewhat correspond to the theory of equations in algebra. So there's no formal definition here what is a mechanical way of doing things, but we know that very often mathematical problem solving is mechanical. You know, when you solve a system with linear equation, you follow an algorithm to solve it. When you solve a quadratic equation, you follow an algorithm to solve it. And Hilbert says this should be applicable in a more general way to all of mathematics. I love the last quote because he talks about his kind of emotional stand. Every mathematician certainly shares the conviction that every mathematical problem is necessarily capable of strict resolution. We hear within us the perpetual call. There is a problem, seek its solution. You can find by pure reason. So if you are stuck on a problem, you're not thinking, oh, well, maybe this problem does not follow from Zermelo-Frankel with choice. You say, I'm not smart enough to solve the problem. This is our normal way to attack a mathematical problem. If I was smart enough, if I came with the right idea, I'll be able to solve it. Pure reason. Kind of the apex of Hilbert's program. In 1930, Hilbert retires, and he was from Königsberg. And the city of Königsberg was very proud of their very famous son, and they made him honorary citizen of the city, invited him to a ceremony, and he gave a radio address. And you can find the recording. The recording is available. And it ends with very famous 6 words. And the 6 words that it ends with is wir müssen wissen, wir werden wissen. We must know, we shall know. And these 6 words, this epitaph is written on his grave. This summarizes his devotion to mathematics. But this is 1930. And in the next few years, Hilbert program, while he's still alive, he died in 1943, while still alive, Hilbert program is completely destroyed. First by Gödel, who proved incompleteness, the first incompleteness theorem. There's no systematic way of solving all mathematical questions. Then the second incompleteness theorem, you cannot prove the consistency of mathematics in mathematics. And then finally, a few years later, Church and Turing proving the indecidability of first-order logic, that the set of all true first-order sentences is not computable. So all 3 legs of Hilbert's program have been shattered just within a few years. So let's first visit Gödel. Gödel was known when he was a boy, he's known as Der Herr Warum, because he was intensely curious, and he always, whatever you explained to him, he always had, yes, but why? Warum, warum, warum? Every answer you say, you know, Why is it dark at night? Well, the sun is set. Yeah, but why? You always ask why. And we can talk a lot about Gödel, but I will just jump to this momentous. I want to remember something. This happened on September 8th of 1930. And a day before that, there is a conference in Königsberg on the epistemology of exact sciences. And there is a panel discussion. And Gödel said this amazing sentence, which it took a while for people to understand. One may in fact exhibit sentences which, although intentionally correct, true, are not provable in the formal system of mathematics. There are lots of questions whether Hilbert was there. Did he hear it? We don't know exactly. The speculation is that he was probably in hotel, busy preparing his radio address, so he may not heard it. He did learn about the theorem later. He never accepted that this deals a fatal blow to his program. He always thought this is some kind of trickery, especially Gödel has this sentence, I'm not provable. He was very skeptical. But for Neumann, who was that a rising star, for Neumann was a prodigy. At age 6, he was multiplying 8-digit numbers in his head and exchanging jokes in classical Greek with his father. He's been working on the consistency of arithmetics, which is Hilbert's second problem. And I realized after that he wasted his time, and he was pretty upset. He was a brilliant man, but very vain man. He knew he was brilliant, and he hated wasted his time. And Gödel outshone him with this result. So he said, I will have nothing more to do with logic. I will never read another paper in logic. Fortunately for us, he didn't quite stick to his promises. Now, the other character I mentioned is Alan Matheson Turing. Most likely, we think today, based on description of Turing, is that he suffered from Asperger's syndrome. And the irony of the Turing test, that if you did a test between a normal human being and Turing probably would not have passed a Turing test, because people would have thought that he behaves robotically. He was behaving robotically. If you have ever seen the TV show, The Big Bang, Sheldon Cooper, the strange physicist who's suspected of being a robot, was very much like Alan Turing. So in these few years in the 1930s, so this is before computers are, or computers are being invented roughly the same time, completely independently. But several people, Church, Gödel, Kleene, post-Turing, you can completely separate the threads, come up with an amazing insight. Remember, the question was, what is a mathematical proof? And the answer was, a mathematical proof has to be so rigorous that checking it should be done mechanically. Coming up with a proof requires creativity. But proof, what is a proof? A proof is evidence which is machine checkable. So this puts computation at the very, very heart of mathematics. The most fundamental concept of mathematics is a proof, and proof required computation. And so for this, we had to define what is computation. We had, of course, people are computing at this point for more than 2,000 years, but nobody ever before that tried to define computation. So a whole theory of computation comes out of it. The concept of algorithm, again, as a mathematical concept, not as a meta-mathematical concept. Turing came up with the distinction between the machine and the instructions, which is, of course, we understand today, the hardware and the software. The concept of universal machine. And today we think that every computer has to be a universal machine, has to be able to execute every program. And even the lambda calculus is still viewed as the Ur programming language, and functional programming languages are very much based on lambda calculus, which was a formalism to describe computation developed by Alonzo Church in the early 30s. Now, amazingly, as I said, this happens by mathematicians who worry about foundational problems. But at about the same time, people are starting to build computers completely independently. So you have Atanasov in the United States, you have Zeus in Germany, and then the first, what we recognize as a fully programmable computer was the ENIACs. Going back to, we can use the term from Leibniz, machina ratiocinatrix, reasoning machine. Here we see Betty Jennings and Frances Bilas programming the ENIAC. To program the ENIAC, you did not write code. You had to set switches and connect cables. If you did one of them wrong, it will not work. It required immense precision and patience. And the conventional wisdom at the time was that only women have this exactness that require for programming. With programming, again, was setting switches and cables. So all the early programmers are women. Later, programming became easier, and that's was when men took over. And now we meet again von Neumann. So we met him when he was 28 years old, and he was in Germany. Now he's in the United States, the Institute for Advanced Studies. He is the last king of mathematics, the person who span across pure mathematics and applied mathematics. And when he was the Institute of Advanced Studies, the joke around was most mathematicians prove what they can. Von Neumann proves what he wants. So he is the great mathematician. And then he was involved in World War II in the Manhattan Project. He was in charge of the computational part of the Manhattan Project. And then after the war, there is a project already starting during the war. The ENIAC is developed in the University of Pennsylvania. The Navy wants to compute ballistic tables. So there is this project in University of Pennsylvania. In 1944, Hermann Goldstein, who was the project manager for the Navy, meets von Neumann in a train station in Maryland, Aberdeen, Maryland. What does he mean? Meets, he sees von Neumann. Of course, he recognizes von Neumann. Von Neumann doesn't know him, but von Neumann is basically the god on earth for mathematicians. So Goldstein goes to him, introduce himself. And like any other mathematicians, von Neumann asks, what are you working on? So Goldstein tell him about the ENIAC. And von Neumann is very excited. He said, I want in. Nobody could say no to von Neumann, so he's in. But at this point in August 44, the ENIAC has been designed. They are just building it. He was not interested in that. He was interested in the next generation, which was called the EDVAC. And in 1946, von Neumann issues a report. The authorship has been controversial since then, but his name is on the report, and it's called a first draft or report on the EDVAC. Subtitle, a preliminary discussion on the logical design of electronic computing instruments. And you can see he did read Boole, he did read Turing. And the proposal is there for what we call today the stored program computer. So we don't have a data store and a program store. We have one store that stores data and programs. This is called the stored program computer. To this very day, we call it von Neumann architecture. And he knew then that this is something very, very important. He said, I'm thinking about something much more important than bombs. I'm thinking about computers. He knew that this is a momentous discovery. So we close the circle. By the early 50s, we have dozens of machines. People call them Joniac because they were built on von Neumann's report. So we have machines built around the world. And Leibniz dream has come true. We have reasoning machines. We went from reasoning to patterns of reasoning. That gave us logic. Logic gave us computing. And finally, we have computers that can reason. And today, of course, computer that can reason is the hot topic of artificial and machine intelligence. But then we discover that the idea of computing is wonderful, but there are lots of problems. We discover that computers are slow, they're hard to program, they're hard to design. And I'll go over each of these problems. What does it mean that they are slow? So take a very simple problem. The students come to ICE. We have colleges. We have to assign the colleges dormitory. We have to assign students to colleges, but they have people they do not want to share an apartment with. So the dean has a list of pairs of incompatible students. So imagine you have to assign 400 students to 3 colleges, and you have a list of incompatible students. How do you find a good assignment? Of course, you all understand this is the 3-color graph coloring problem with 3 colors, but the number of combinations is astronomical. It 10 to the 200. So if you have a very fast machine, you do billion assignment per second, it will take 1,000 years to solve it for 40 students. For 400 students, it will be longer than the lifetime of the universe. So by brute force, there's no way you can ever build such a machine. So if the idea is, okay, we just need faster computers, no, this is not going to be a solution. So is there a better way of doing this? This is kind of the big question. Maybe we're just not smart enough. And this realization that many problems are only amenable to exhaustive search. Exhaustive search is so slow that it doesn't matter how fast computers are, they will never be fast enough to solve it. The first research program on this line is in the Soviet Union in the 1950s. It was called the Perebor problem. I always wonder about what does the fact that Russian have such a short word for the term exhaustive search or brute force search, what does it tell us about the culture? So there was a research program that was cutting edge, but did not ultimately yield results because they did not have positive results, they did not have negative results. In fact, we found out that the difficulty of Boolean reasoning was already observed by people in the 19th century. Remember, we saw Gibbons, even Boole himself, there are some exercises where, you know, you're just dealing with 4 propositions, or 5 propositions, A, B, C, D, E, but it's just really tricky. You try to model it, you write a formula, you try to do it. Boole already realized that Boolean reasoning is very difficult. And in fact, the only one way to do that in some sense was exhaustive search. Now, a beautiful insight that came up in 1971 was that the coloring problem is easy to find as an assignment, but if somebody gives you an assignment, you can very easily check by just going over all the pairs of incompatible students to see if there's any violation. So you can very easily check an assignment. Similarly, if somebody gives you an assignment, is it satisfying assignment? If somebody gives you a solution to this problem, you can check it very easily, but solving is hard. And so today we think of P are the problem you can solve easily, and P are the problem that have short proof that can be checked efficiently. So our concept, you say, if the proofs are too long or too difficult to check, they're not very useful. So NP is a class of problems that have feasible proofs. And this became $1 million question. Literally, there is an award. The Clay Institute has an award if you prove if that P equal or not equal NP. And in 1971, Leonid Levin in Soviet Union and Steve Cook in the United States independently proved that P equal NP, if and only if Boolean reasoning, P is indifferent than NP, if and only if Boolean reasoning is truly hard. So logic is not only the heart of computation, but logic is at the heart of computational complexity theory. So the first problem to prove to be NP complete was logical reasoning is NP complete. I also said that programming is hard. So suppose you want something very simple. What Rice professor does John Smith take classes from? So we saw that on the ENIAC, to answer this question, you had to set up switches and connect cables. Very difficult. Later on, people discovered we are going to write code. And how did you write code? Well, machine language. This is how you write code. So here you see code in hexadecimal. Hexadecimal was a high-level language because a low-level language was binary. So people discovered this is very difficult to write code like that. So we had to invent better and better languages. So today we have, this is a piece of code in C. And you can look at it and say, oh, this is still very, very unfriendly. So we know today that writing code is hard, lots of bugs. So this is still not satisfying. So why is it so hard? So we realized that actually a long time ago, the problem with computer is that they are idiot savant. You have to tell them exactly what to do. You have to tell them precisely what to do. You know, you can't, there could be no ambiguity. We humans speak in natural language, but natural language is very ambiguous. Look at this simple sentence. I only borrowed his car. 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 Just putting the stress completely change the meaning of the sentence. So what does this sentence even mean? So we want a language that will be close to natural language, but will have very precise meaning. And in 1970, Ted Code says, let's use first-order logic as a query language. So we said, we have a language, it had precise syntax, it's precise semantics, there's no ambiguity. And if you want to say, give me all the professors who are teaching, all the course students that John Smith is teaching, you say, you write a sentence, you said, you quantify over the courses, you said John Smith is taking a course Z, and Z is taught by some professor. So SQL today is essentially user-friendly syntax for first-order logic. The language designed by people so that secretaries will be able to write queries in SQL. Didn't quite happen that way, but it is still really essentially first-order logic with some second-order addition that I will not get into. Okay, so logic had a huge success not only in circuit design, but logic gave rise to relational database theory, which I think is a neighborhood of a business of $50 billion a year business. And the final point is people discovered that designing machines is actually very hard. The Pentium had 3 million transistors. A current iPhone has 12 billion transistors. When the Pentium was released, turns out there was a floating point division error and design error. And Intel had to recall the chip, and it cost them $500 million. Today, it will cost them easily, such a bug, $10 billion. So how do we ensure that the design that we issue when we build chips, they really do what we want them to do? Again, we need to describe the behavior formally, rigorously, and then algorithmically check the design meet the specification. So we need a logic to describe behavior. And classical logic was static. It described one moment in time. And already, logic is timeless. But even Peirce says, what about time? And then in the 1950s, Arthur Norman Pryor in Christchurch, New Zealand, developed tense logic, became known later as temporal logic. And then in 1977, Amir Pnoeli proposed to use it to describe behavior of computer systems. For example, you want to say if a message is sent, it will be received. And now you use temporal logic. You say always sent. I mean, there is a parenthesis error here. I apologize. Always sent implies eventually received. And in fact, today there are industrial specification languages that are based on temporal logic. So today they are industry standard. So this went from philosophy again to industrial usage. So in summary, we have seen how logic and computation are joined at the hip at the foundation of mathematics. But my point is that this connection has continued for the past 50 years. And today logic plays a central role in computer science. Some people have called logic the calculus of computer science. Is the same way that if you're doing civil engineering, you're using calculus as your fundamental mathematical language. And in computer science, we use logic very often in this way. And in fact, I would even argue, and this I know I will be somewhat provocative in this argument, logic had been much more effective in computer science than it had been in mathematics. Because the question is, okay, there are people who do mathematical logic, and I'm sure many of them are here in VvL, but what impact does it have on I would say, on the standard working, practicing mathematician? There's now some talk about formalized mathematics. This is emerging area, and maybe logic will have a large impact on mathematics. But what I try to show, logic has already huge impact on computer science. And we'll go back to Cosma Arshalizi from the Santa Fe Institute, who wrote, in one extremely important field, however, it, meaning logic, reigns supreme, and that is computation. Programming is simply mathematical logic in action. The melding of theory and practice is so complete that most practitioners have no idea that their speech, recursion, lexical scope, data abstraction, even those bands of C novices, pointers, referencing, dereferencing, this is all, he called it logical prose. I'm a little behind, so I'm going to jump to the very end, and I'll finish with a joke due to Smulian. Two logicians in a conference are seeing they enter a room, there's a blackboard, on in it is written, only an idiot would believe a sentence like this. They look at it, they're puzzled. One logician asks the other one, do you believe this sentence? The other one says, of course not. Only an idiot would believe a sentence like that. Thank you very much.
Thank you very much, Moshe, for this inspiring talk. I will ask you also on mute so we can give Moshe an audio applause. I think that's much nicer than we can also clap, of course, in the hands. Okay, so before we open the Q&A to the audience, we will first have a round of comments and questions from our three commentators that I will briefly introduce now. Well, first, we have Marieke Hausmann, who is a professor of software reliability at the University of Twente, where she leads the formal methods and tools group. She was awarded the Dutch ICT Prize in 2013 for her innovative research on formal program verification and reliability of concurrent and distributed systems. And she was also the recipient of an ERC starting grant and an NWO VG grant. And she is currently the president of the ETAPS Association. And until recently, she served as the chair of VERSEN, the Dutch National Association for Software Engineering. So thank you very much for joining us today, Marieke. Next up, we will have Frank van Harmelen, who is a professor in knowledge representation and reasoning at the Vrije Universiteit Amsterdam, where he leads the knowledge representation and reasoning group. And he has played a leading role in the development of the semantic web. And currently he is a PI of the gravitation project Hybrid Intelligence. He's a fellow of the European AI Society ECAI and a member of the Academia Europaea and the KNAW, the Royal Netherlands Society of Sciences and Humanities. Thank you very much for joining us, Frank. And last but not least, we have Johan van Bentem, who is Emeritus University Professor of the University of Amsterdam and Professor at Stanford University and Tsinghua University. Johan is one of the most prominent logicians of our time with his groundbreaking contributions to logic and its applications in language philosophy, computer science, and cognition. He's also the founding director of the ILLC at the University of Amsterdam, and he has received numerous distinctions, including the Dutch Spinoza Award, memberships of the KNAW and the Academia Europaea and the American Academy of Arts and Sciences. He's also an honorary member of the VvL since 2014. So thank you very much for joining us today, Johan. So I would like to start by giving the word to Marieke Hausmann. Please, Marieke, you should be able to unmute yourself.
Yes, thank you. Thank you, Helle. And thanks for the nice introduction. I wanted to show a little booklet. I thought Moshe gave a very nice talk, but if you want to know about the missing part in his story, well, he had one picture where he showed a few women how they were programmed the ENIAC. If you want to know more about all the other women who worked on logic and computer science, search for Alice and Eve. You get 25 women and their contributions in computer science. Sorry, I had to do that after this talk.
Oh, that's really nice. I didn't know about this, so thanks a lot.
Yeah, and I'll also be happy to send paper copies if you're interested, but I'll share the link afterwards. But what I was wondering, I thought your talk was very interesting, Moshe, but it made me wonder. So what we see is that there is this digital transformation, computer science is changing. And in particular, if I look at our students, I think the amount of logic that they get actually is diminishing. And I was wondering, are we making a mistake there? I think you're muted.
Yes, I think we are making a mistake. I think deep learning has had revolutionary success over the past decade or so, and it is shown to be incredibly powerful. It's an idea that you go back to Pitts and McCullough in 1943, I think, the paper that first proposed neural nets. It's a paper in logic. And you go to von Neumann's paper, and he's quoting Pitts and McCullough also. Okay, so we need to understand. AI had waves, and every wave there is tremendous amount of hype, and everybody said now we have the right idea, and all the other ideas have been worthless. And so every idea somehow, every generation tried to dismiss the previous generation. But in reality, all of the ideas of AI cumulatively give us growing understanding of knowledge. The first wave of AI gave us logical reasoning. And in fact, I recently saw a paper that tried to train a neural net on solving Sudoku where the numbers are written by hand. Mm-hmm. So you need both to recognize digits, but also you need to do the logic underlying Sudoku. And so actually what they had to devise an architecture that try to uncover the logic of Sudoku. Imagine trying to solve Sudoku just purely by looking at pixel without understanding the logic, okay? And so the answer is that, and some people, in fact, go back today and you say, you go back to Kahneman, who tried to describe intelligence, and he says, well, the human brain has the part, what we call the lizard brain, and lizards are not, we're not that much better than lizards in pattern recognition. A huge part of what we do in life is recognizing patterns, okay? So face recognition, we don't look at someone and say, oh, this is, except with me, somebody said there is a mustache and no hair, so it must be Moshe. But usually we just recognize it. You know, it's fast thinking. That's what they call fast thinking. So if you're walking in the African savannah, you see the grass moving, you see something yellow moving, you say, oh, I need to run away. This is probably a lion. But then you go back to your village and say, we need to hunt the lion. Now you need to make a plan. Now, this is slow thinking. And human intelligence has succeeded in combining them, not always harmoniously. I mean, we all know, for example, that the brain says, you know, eat the ice cream, eat the cookie because you want it, you want the calorie. The forebrain says you don't need a calorie. And it's a struggle for us sometimes to reconcile these two parts. But overall, is we are, when we are driving, we recognize a stop sign. That's a pattern recognition. We know that a stop sign means stop. And that's why we stop. We have symbolic knowledge and we say this means stop, so you're going to stop. And so I think one of the great challenges now is neurosymbolic reasoning. And in fact, you can see there are lots of papers now on neurosymbolic reasoning. And people are saying, can we take all the legs of AI that we had, which was symbolic reasoning, probabilistic reasoning, and now deep learning, and somehow find a way of doing synthesis. Still, if you're going to, you know, when you look at programming languages that employers want, somewhere in the top 3, almost always, you find SQL. SQL is enormously useful language. And yes, you can learn it without logic. But if you know a little logic, then you can think better. Mm-hmm. Not to mention that, you know, why do we teach students plane geometry today? They're not going to divide fields, okay? We want them to think exact reasoning, okay? And part of, you know, and computer science is very much about formal descriptions, and logic is the study of formal descriptions. So I think that, you know, there are computer science, we always go through waves of hype. There is what's called the hype cycle. We're already, I think, a bit going from the top of, from the peak. We should recognize deep learning for revolutionary success. We should ask, how do we integrate it with other things that we have learned?
But then if we get the quantum computer?
Let's talk about quantum computers when we get there. I'm known as a quantum skeptic. Not that it's not that I'm skeptical of some people are skeptical of the technology. I'm skeptical of the business case, but that's a whole other topic.
Okay, yeah. And from what you're saying, should we actually teach logic to everybody, not just to computer scientists?
So there is a project that followed by some folks at Stanford. They think that in some sense that the plane geometry being part of mathematics today is misguided. And what I mean by that, if you look at it, teaching, for example, algebra and calculus in college, students will go on to any part of almost in the science and engineering. That part will be very useful indeed. That part of they will use algebra, they will use calculus. Who's going to use plane geometry? It's that we're really trying to teach students when we teach them plane geometry is exact reasoning. We're really trying to teach them logic. So why are we teaching them plane geometry? Well, which even the teacher don't know why they're teaching, other than it's in the syllabus, so it's in the curriculum, so you must teach it. Let's understand that really the reason it was introduced into the curriculum as a way to teach deductive reasoning. And so let's just go back to fundamentals and think, what do we need students? We need to teach students, in some sense, logic, or I would say exact reasoning, okay? So do we need to teach them everybody precisely propositional logic and first order logic? Maybe, but we need to think, how do we teach exact reasoning to the masses? That I think is, I think this is very much on target.
Yeah. Okay, so maybe Hella, I should give the floor to Frank.
Yes, so if because we're a little behind, I would like to make a first round, and then we come back again, and you can all join in a joint discussion. So thanks a lot, Marieke, and then I would like to give the word to Frank van Harmelen.
Thanks. Hi, Moshe, and thanks again for your very both inspiring and entertaining lecture. I want to pick up the point that you made about AI. As you said, most of the disruptive innovation in modern computer science, a large part of that comes from AI, and a large part of that in the last 10 years comes from machine learning. And machine learning is actually not helped mostly by logic, but it's mostly helped by calculus. Right? Machine learning is about differentiable functions. It's about high-dimensional differentiable surfaces. So isn't logic missing a beat here? Shouldn't logicians worry more about, say, differentiable logical operators rather than the traditional discrete operators that logicians were studying? Is logic still relevant to modern computer science, or should it really take continuity a little bit more seriously?
So von Neumann already complained. I'm just opening Alice and Eve because I really want to learn about it. So von Neumann already complained that he said that logic is very discrete. He said the power of, he didn't like discrete mathematics. He just loved the power of analysis. And discrete mathematics, he didn't quite like it. So we have an issue with logic that it's just too binary. It's just 0 and 1. And so part of the question is, how do we take, what do we need to make logic more, not just qualitative, true and false, but more quantitative? And there are different directions this takes. For example, one line of research, and other people, and I'm also involved in it, instead of looking at a Boolean formula, we ask, is it satisfiable or not satisfiable? Now we want to know how satisfiable is it? That is to say, how many satisfying assignments does it have? So this became known as model counting, and now it's quantitative. And it turns out that this actually has lots of applications. This become very, it come lessons, I would say, that the kind of logic community, but from the AI community, because it turns out when you do probabilistic inference, you can encode it as a model counting problem. So this is one way where we take logic, we make it more quantitative. The other one had to do with the fact that differentiability. So again, we can. I have a PhD student who's now working on trying to use continuous optimization techniques to solve discrete problem in logic. So the question is, can we look at in logic, and can we start using calculus to reason about logic? So all these questions are really good, and in fact, one of the things that we did learn for machine learning is the importance of bringing in continuous method. One of the reasons that machine learning has been so successful is suddenly think that I have to go back to remember calculus, graduate descent and things like that. So we need to integrate this, and we need to start thinking about logic, not just 0 and 1, but more quantitatively in different ways. And I think this is very much kind of cutting edge of research right now to think of logic in a more holistic way.
So there was something that I missed. You give a presentation to the Dutch Association of Logic, right? And of course, the Netherlands and Amsterdam in particular is one of the birthplaces of constructive logic. And there is a very intimate connection between constructive logic and computing. And essentially, a constructive proof is an algorithm. So was this because of lack of time that you didn't mention this, or is this because you don't see an interesting influence or a promise there? Could you elaborate?
No, I think it needs somebody needs to do this project, but it has to go back to, I made a hint there about the war between Hilbert and Brouwer.
Yes.
And you go to the whole issue of constructive mathematics and what role does it play. And this could be, I would say, is a whole other talk would be constructive mathematics and computation. There are people who argue that it must be, we should only deal with constructive logic, but that's, I think, a bit too one-sided to me. But there's no question, in many cases, we have major applications of constructive logic. And, I mean, even if you look at intuitionism, There are people who do use it. I mean, there are people who try to do intuition set theory. So we still have all these things again. Instead of think of what happened in physics. So we said, okay, the Newtonian model is no. We have general relativity. Really? We go to the moon. How do we go to the moon? We go to the moon using Newtonian mechanics. So I think we need to, instead of just saying we throw away, that these people complain about Kuhn's scientific revolutions, think of paradigm shift, and we throw away the old paradigm. The answer is really no. In science, you rarely throw away the old paradigm. You say old paradigm was not accurate enough. Let's refine it. So if you are going very fast, then we need to think of relativistic effects. Okay. So when we do GPS, we need to think about relativistic effect. By going to the moon and landing on the moon, we don't need relativistic effects. We just use Newtonian mechanics. So he said, the old theory, most of the time, we don't throw them away unless they are completely wrong. We don't throw them away, we build on it. And I think the same thing we need to do here. So constructive logic to me does not, I don't throw away classical logic, but I find when is it applicable and when do you do that? And there is a beautiful thing we can get out of it. For example, if you talk to Bob Constable, this whole idea of programming by proof. You prove it, and the proof is a program because the proof is constructive. It tells you how to get the object. So there's just a whole other talk I can give just on that.
Okay, great. Thank you. I'll seize the floor to Johan.
Thank you, Frank. Thank you very much. Yes, so next, Johan van Bensum, please, you can unmute yourself now.
Okay, I hope you can hear me.
Yes,
I was the victim of a strange combination, I guess, of self-reference and maybe computer science is not so great as all you guys have been saying since the connection dropped exactly at the moment I had to say something. So just very briefly, because I'm sure the audience will have a lot to say. So Moshe, great talk. I really like this historical perspective. In fact, this is the sort of story that I think students should know about and so on. And I was reminded a bit of a book in my student days, which I liked a lot, by Maurice Klein, The Role of Mathematics in Western Culture, where you would actually get a sort of historical and cultural perspective and see what mathematics actually did there. It would be great to have a sort of similar book for logic. But I guess your slides are only the sort of outline for that book, unless you're aware of a text that will do the job.
There is a book, but not to the full extent, but there is a book by Martin Davis that covers some of this stuff.
Okay.
Yeah.
Then my second question, more about, of course, there is the frivolous point that if logic begats computer science, you wonder who with. And actually, but maybe the serious question is, what sort of combinations of fields do you think created the liveliest intellectual atmosphere? Because, let me elaborate a bit on that. Your story starts in the grand foundational tradition, or well, it doesn't start there, but its sort of high point is the early 20th century. And then we're talking about questions that have a lot of different motivations, right? And in particular, what's also so mysterious and exciting about that period is a sort of mixture of positive and negative results, right? You could say the high point of Turing's paper was actually to show that a very reasonable question is not computable, namely the halting problem. But somehow I felt that these grand questions drop out a bit when you talk about all the successes of logic and computer science, because then you start saying it's good for this, it's good for that. It's like aspirin, you know, like any headache that computer scientists might have is going to be solved. But what about the grand narrative, things you can compute, cannot compute, and maybe even a joint engagement in the big foundational questions?
So, I mean, in some sense, I think that Turing gave us the answer on the kind of these fundamental questions of what can be computed. I think that there is a big question today, and I don't know that we know how to address it, is what can be intelligentified. Let me kind of coin a word for that. What is the limit of machine intelligence? And I think that's a big question. I don't see it much being kind of addressed. We don't have a good mathematics for it, and we have all the way from, I would say, that the prophets of doom that superintelligence is about to take us and treat all of us as paper clips, as dispensable material for paper clips production, which is kind of one thing. And I think actually, in some sense, if you ask me today, what is the biggest question in today, I think for us is to understand the impact that, and this was actually, I gave a talk just about yesterday, the impact of computing on society. I think we have been a bit of nerds to say, oh, we just do the computing, other people will worry about the impact on society. And if all we did was publish papers, then okay, fine, okay. But the answer is that we're not just publishing paper. You know, the image, you know, there is a science fiction novel from the 80s, Ender's Game, that I read it when my son, I had a teenage son, which I found difficult to talk to, but if I read his book, I could talk to him about the book that he was reading. So I started reading all his books. And this is a bit of spoiler alert here. And there is a boy who's playing video game with his friends, and he doesn't realize that he's really fighting an intergalactic war. And when he wins a video game, he actually destroys a whole civilization. And to me, this is a little bit like us now. We've been playing with computer. It was fun. We made a good career out of it. You know, the pay is good. So we're having a good life. But this is for real. Real products are using this technology. Real products are being deployed. They are changing the world. And we are saying, oh my, we really just wanted to have fun. And look what we have done now. And how do we deal? What responsibility do we have to what happened? And, you know, we can go back and analyze it. But one answer is, I think we were naive. Again, we're not unique. I mean, there are stories about, I said, the British physicists who thought the electron, who will ever need to use electrons? And so we did not foresee the consequences of what we have done. Actually, for Neumann had another quote that he says, you know, that this is the kind of the last invention type of quote, saying that it's not that computing may destroy humanity. And so he did see that there are great risks, but it didn't stop him. It didn't stop many people. And I think now, in some sense, the genie is out of the bottle. So to me, there is a question which is not a scientific. Well, I don't know, it's a scientific, but in a broader sense, which is required understanding social science. How do we live with technology? And this will not succumb to beautiful logical theory. This will succumb to messy social science. I don't hear Johan.
Yeah, Johan, I don't. Looks like he has lost connection. Is he frozen again? Yeah. Okay. Yeah. Oh, that's a pity. Oh, well, let's hope he may join in. Yeah, I was going to open up to a joint discussion of the commentators. I don't know, Marieke, Frank, would you like to come back on some of the points that were discussed before we open to the public?
Yeah, open to the public, I would suggest.
Okay.
I'm sure there are lots of questions.
Yes.
Wisdom of the crowd.
Yes. So indeed, now the audience can ask questions, and I would like to ask you to use the raise hand function. I see already one hand. I have here Wim Martens, and you should be able, let me see. I'm clicking ask for mute.
Yeah.
Are you able to unmute yourself? Yeah.
Yes, hello, hi Moshe. I want to preface this question by saying that it does not happen very often that a talk has some moment in which I get goosebumps, but today it actually happened a couple of times and I'm very happy for that. I wanted to ask you, actually it's a bit of a follow-up to the last question. So I wanted to ask about the connection between your talk today and the talk yesterday, because if you look at the material from today, I mean, what you presented now, a world filled with difficult questions and in which many logicians and computer scientists feel very comfortable, right? I mean, this is the crowd that you're talking to today. And now, yesterday you discussed in this Gödel lecture a world which is a real world full with problems and questions that are immensely important for our society, but as it seems much less easy to tackle with the tools that we have. And I was wondering how you see the balance between the two. I mean, on the one hand, we have this crowd here, which has an amazing intellectual capacity, but we feel comfortable in our own world, yeah. And how, yeah, should we invest more time in thinking about solving these really important society questions?
So yeah, I think that's an excellent question. It comes back again and again. What should, I mean, very often people ask me, what should I do? Okay, and I'm trying to personalize it. What should I do? Students ask me these questions. What should I do? So first, my point is that to me, the story of humanity is living on the what's called the knife's edge of technology. I mean, if you look at really where we, you know, if you look at where were we about 1 million years ago? Well, just in yet another kind of type of ape. But this ape discovered technology, and technology also drove evolution. And so we discover fire, we discover, you know, projectile weapons, we invented technology. And every technology always has the helpful. We use fire to cook. People still die from fire. I mean, fire is still a mortal threat to people, especially now. You hear it on the West Coast. We have greater, and we're just heading now into another summer on the West Coast. We'll have 6 months of fires on the West Coast in the United States. So the story, I would say, of human civilization to me is the story of how can we live with technology. And right now, if you look at the biggest threat on humanity is actually not computing, is climate change, which is again has been caused by technology, right? By carbon-based energy, and it's now we're making this planet inhabitable. And so that's kind of part of the human story. Now, scientific fields went through such a moment, like a Ender's Game moment, like that, where they discover, oh my God, what have we done? You know, you read stories about a German chemist whose research led to chemical weapons in World War II. Not to mention later on even the gas chambers in Auschwitz. But even in World War I, the chemical weapons. And this chemist says, "Oh my God, what have we done? How do we deal with this responsibility?" Physicists have the same moment after World War II with atomic weapons. And in each case, people didn't say the solution is to stop doing physics. People said the solution is to try to face the problems heads on. You know, there is a organization, Union of Concerned Scientists. The physicists came up with something called the Bulletin of Atomic Physicists. And they tried to look at this, to have a conversation. They say, we're not going to solve the problem by our own, but let's have a conversation with other disciplines. You have, for example, all the way Robert Oppenheimer, who was in charge of the Manhattan Project, was a huge fight. He objected to development of the hydrogen bomb, of the fusion bomb. And so there is a story of scientists being involved in the discussion, in the public discussions about technology. And that requires us to get out of our comfort zone, okay? So I kind of step a little bit into economics. And I discovered there is just a lot of mythology. You go to the economists and there is the theorem. The theorems are theorem of mathematical models. To say that this applies to the real world is a huge jump. And I did not hesitate even to argue with economists. I can argue with them always about the basic theory, but I said, does it apply? For example, there is somehow dogma among many economists that the real market works. So if people lose their job because of automation, they will find other jobs. But it turns out that this is not even good economics. It's just bad economics. But it does require us to get out of our comfort zone. And students ask me, what should I do? And I tell students, you have more power than you can think. You have power, first of all, with your fingers. You're a voter. You're a citizen. You have to, there will be there are good policies and bad policies. There are good politicians and bad politicians. And the first thing when you say, what should you do? I said, vote. Especially here, voting by younger people has been rather low. And I said, the first thing you should do is vote. The second thing I tell people, you can vote with your feet. What does it mean? Take Rice students now. When they get a bachelor degree from Rice, which is a fantastic reputation undergraduate school, they get fantastic job offers. They can write their own ticket. They have a choice where they go to work, okay? They can say, and so we teach a course on ethics, and if you're interested, you can go to my webpage and you'll find a course that we call Deep Tech Ethics. We teach this course on ethics and accountability in computing. And in one of the courses, I did a poll among students, anonymous poll. If you get an offer from Facebook, will you go to work there? And 2/3 said yes, and 1/3 said no. And I said, is any one of the yes willing to speak up? And somebody did, said, it's going to be a well-paying job, lots of smart colleagues, interesting technical problems, I'm in. And then I said, is any one of the nays willing to speak up? And somebody said, yes. Why would you not take a job at Facebook? And he said, I'm sure I'll have many job offers. Why should I take the ethically questionable one? There are other companies that do things that are not questionable. I'll go to that company. There is a bit of a upheaval. If I don't know if you're following what's happening inside Google. Google is a company whose basic business model is surveillance capitalism, which I find very unethical, but completely legal. But at the same time, they're trying to say, we are a very ethical company. We do ethical AI. We do responsible AI. And that caused this contradiction is something they have not been able, they have cognitive dissonance. So they write papers and they say, no, you cannot publish the paper. People are fired and people are resigning. A major conference on fairness, accountability, transparency, whatever in computing decided to kick Google as a sponsor. This is kind of unheard of. Somebody is willing to give you money and the conference says, no, your money is contaminated to us. We don't want your money. Get off. We don't want you as a sponsor. The main asset of these companies is the workforce, is whatever, it's not the fact that they have data center. If it becomes, I mean, look what happened to one of the things that we have not made progress in nuclear energy is because nuclear has a kind of a dirty reputation. And it didn't attract, people don't want to become professionals in nuclear engineering. And so the field has not made progress, partly because of their reputation. It's quite possible that some companies will suffer if they end up, having this negative reputation. So students, I don't tell students, go to work on Facebook, do not go to work for Facebook. We talk about ethics, we talk about responsibility. They have to make their own decision at the end. But I think we all need to understand that our technology has consequences. And do we have quick and easy answer for that? No, this is not mathematics. You don't have a nice, elegant proof for these questions.
Thank you. Would you like to follow up, Wim? Or otherwise, let's see if there are any other questions. So I don't see any raised hands at the moment. So I see Johan is still here. I was going to ask Johan if he wanted to follow up, but he has connectivity issues. So I don't know if it's, yeah, it's up to you, Johan, if you would like to give it a try again.
So, because this issue is also, like when I had more interactions with our computer science department, the following question would often come up. So logic is a sort of a long discipline, and as I said, it has played a large cultural role. Like, right, you can see its influence, of course, in computer science, but also in philosophy and linguistics and so on. And computer science, at least it looked at the time, had a sort of culture problem in the sense that many people see it as an engineering discipline, and not so much as a supplier of very fundamental and basic ideas. But now let me go out on a limb and say, I actually think computer science is as interesting as logic or mathematics as a supplier of major cultural ideas, not just getting things done technologically, but also in shaping our thinking about what the world is like. And I wondered whether you have any views on this cultural role of computer science and whether a sort of linkage between logic and computer science could actually be effective there. To give an example, the chairman of our computer science department in the 1980s, whose name I won't mention, once told me that a paper I'd written on logic and computer science had saved his day because he had actually had a meeting with the president of Amsterdam University to make a plea for the importance of the computer science department. So he had given all the usual reasons, we'll make the computers faster, we'll do this engineering thing and that. And then the president actually said, yeah, that's okay, but why would that make you important as a discipline in the university? And then the chairman said, but then I suddenly remembered one of those vague and hazy papers of yours about the cultural role that computer science could play. So I cited a few sentences from that, and then the president said, now I see, it's really important. It could shape the way we think, change the way we think. With that long preamble, do you have a view on the cultural role of computer science?
So I think I completely agree with you. I think we are still not fully understanding the significance of what we have done here. So some people describe what has happened over the past, 7 years, the information revolution. But think what it means. It means that a very nebulous concept, information, knowledge, reasoning, these are all very nebulous concepts, which these are concrete objects. You can quantify them, you can abstract them, you can manipulate them, you can store them, you can process them. We took this, one of the most nebulous concepts of humanity, something that people would think, epistemology, right? It's a bunch of philosophy. And now we can do computational epistemology. And so the idea of the information revolution is we take this very nebulous concept, and which you thought would be just an abstraction, and we're able to quantify this. Imagine somebody would say, I can take another one, I can take love, and I can quantify it and manipulate it and process it and do things with it. Maybe one day people will do it and we'll have the love revolution. But right now we've done information revolution. What is the university about? The university is about that. It's about knowledge, about information, about reasoning. And this is the one discipline that says we have been able to put our hands around that concept and manipulate it as if this is a concrete thing, not some fuzzy philosophical thing. This is, now companies are now start talk about it, about the digital revolution, and you talk about digitalization, and it's kind of goes in the same direction. They suddenly understand that all these things that have been floating around, the knowledge of the corporation, all of this can be codified and manipulated and learned from and acted on. And that's why, you have, if you look now, you can just Google and you find people talk about the fourth industrial revolution. And it's all about that, is how to take this knowledge that was kind of floating around in a corporation and make it very concrete and manipulate it. So I think this is a revolution of immense consequences. So, I mean, we kind of have done, if you look at the cultural revolution, right? What are the cultural revolution? We're somewhere around, maybe 500,000 years ago, or between 500,000 and 1 million years ago, we discovered speech. Amazing. I mean, probably one of the biggest human invention, right? We can talk and communicate. And then very recently in human history, extremely recently, like 6,000 years ago, we discovered writing. So this was the first step of taking information and suddenly codifying it, getting ahead, making it more concrete, which was a huge, I mean, if you think about it, this is where human history starts. Before that is prehistory. Once we can write, this is the beginning of history. And now we've gone the ultimate step, which is information is quantitative, it's manipulable, it's processable. And the consequences of that, I said, I should have put, this other quote by von Neumann, who basically viewed it as a huge milestone for humanity to do that. And I don't think we have fully internalized and grasped this kind of thing. And partly because very often as computer scientists, we are playing the role of nerds. We're just looking, I will do graph reachability. And we have yet to fully understand, to me, this epochal, life-changing kind of a revolutionary thing if we have captured information, knowledge, and reasoning, and we're the discipline that studies how to do that.
Okay. I couldn't agree more, and thank you.
So I also think that you can see this in broad culture. Now, the dominant culture, the dominant metaphor of what we are, our brain, the dominant metaphor now is a computer. We are thinking about organizations as information processing machines.
Even life. Some people are trying to push the paradigm that even what an organism is some kind of information processing.
And you see this across sciences. I think many sciences will turn out to be applications of computer science.
Yeah, and then there are people who do serious research, like Papa Dimitriou, I think, has done fantastic work on what they call computational lens, look outside of computing, and he has really amazing results. For example, economists have all the theorems about equilibria, and essentially what Papa Dimitriou and his colleague has shown that it takes exponentially long to reach equilibrium. which means in practice, you never reach equilibrium. It just takes too long. And because it takes so long, circumstances will change. You fixed all the inputs, and then it takes exponential many steps to reach equilibrium, but there's no way all these inputs will stay fixed for that long. So all this economic theory about equilibria, it's all beautiful abstraction, but in reality, the economy is never in equilibrium. And this is, again, this is an insight that comes from computation. So that's partly there. It's a fuzzy concept that people are trying to promote computational thinking. And I don't think we fully understand it yet, but I think that, I mean, I have a whole idea that computation lies at the heart of the philosophy of science, but I don't want to get into it right now.
Okay, thank you. So I see there's also a question from Pesofen and de Boers. Please go ahead, Peter. Can you unmute yourself?
Am I hearable now?
Yes.
Yes.
Good, thanks. It was a great talk, except for the fact that I had heard it before when you gave it for ACM in a tech talk. But I like to use this opportunity to probe you on the question of the next big thing in theoretical computer science. And what I'm referring to are two things. One which happened about 40 years ago, when people realized that thinking about distributed computation in the anthropomorphic terms, people discovered that they were talking about knowledge, and that gave rise to epistemic knowledge becoming transformed from a branch of esoteric philosophical logic into a hardcore business in computer science. And you have, I know you have contributed a lot to that field. The second thing is something you just mentioned that happened when people were, again, from the distributed perspective, were thinking on strategic interaction, and suddenly, lo and behold, game theory and economical theory became a major important branch. That happened about 20 years ago. So here is my challenge. Do you see a comparable next big thing appearing, let's say, in the forthcoming years?
So I think that the success of deep learning is forcing many people to pay attention. And one question is that the same way that I quoted Wigner, who talked about the unusual effectiveness of mathematics in the natural sciences, the success of deep learning is somewhat of a mystery. Again, it was I mean, the interesting thing about this, it's an old idea. It goes back to Pitts and McCullough, and there are waves of up and down over the years about it. And I heard the story from a colleague who said he remembers in NIPS 2000, or it was NIPS and NeuroIPS now, he saw Jeff Hinton standing in the corner during a reception, and nobody talks to him because he's the crazy guy that still believes in neural networks. Well, everyone else at NIPS, okay, neural information processing system at the conference gave up on neural networks already, and he still believed in it. And somehow what people really miss to understand that training neural network takes a lot of computational effort. So we had to have better hardware and better algorithm, and most importantly, lots of data. And suddenly that's launched a revolution. And we don't fully understand this. Why are neural networks so effective? And what else can we do with them? So there's a whole new line of work starting just emerge over the last couple of years to use machine learning for algorithm design. If neural nets are so successful, can we use them for algorithm design? And people are now using this whole graph neural network, GNNs, and people use them for lots of optimization, graph optimization problem and showing effectiveness. But much of it is, I would say, either not very good theory or very empirical sometimes. And it's crying for better, stronger mathematical theory. So I think if the hottest thing right now is deep learning, the hottest theory should be the theory of deep learning, trying to put it on solid theoretical foundation, which right now is sorely missing.
The preamble question is to understand what it's really doing.
Yeah, absolutely. We don't know what
every week I'm reading documents and theses submitted using deep learning. And they are achieving marvelous things with it, but there is no understanding what actually achieves.
The other, I think, thing that is just emerging right now is based on the theory of computability, we developed this beautiful theory of computational complexity theory. And I would say that intellectually, it is one of the kind of the apex of, and it's tightly connected to logic, as I try to show, and it's just a gorgeous mathematical theory. But
that was the major big things from 60 years ago.
But what we have learned since then is that we have done one idealization that was incredibly huge consequences, which is worst case complexity analysis. And when we actually try to solve problems in the real world, so, you know, there is a whole other talk that I could have mentioned, I could have spoken here for another hour. The Boolean satisfiability, which is NP hard, does not seem to be so hard in practice. We don't understand it why. And we discovered the NP complete problem may be hard in theory, and they have hard instances, but they don't seem to be so hard in practice. So there's a whole line of work now just starting in the theory community. And in fact, Tim Raffgartner just edited a book, a handbook on beyond worst case complexity. Lots of people are now trying to say, okay, what complexity give us very idealized measure. It's not good enough to predict how things will be in the real world. Do we have a better understanding? And this is just emerging. And there is no theory yet that emerges there. There are many attempts to do that. I encourage you to look at this. It's a thick volume by Tim Raffgartner, edited it. I encourage you to look at it. And he also wrote a CSM article a couple of years ago on the topic. Whether it will succeed or not in both cases, you know, I think there is a crying need for a good theory there. We'll have to wait and see what happens. I remember somebody once asked Stephen Hawking, what is the best paper in physics this year? And his answer was, ask me again in 10 years. So let's talk about it again in 10 years.
Okay, if we then still are around, I'll like to chat with you about it.
Yeah.
Thanks.
Okay, I'll send you a Zoom invite.
Thank you. Yes, I think it's also time to move to the more informal part of the interaction in GatherTown. I just want to mention that your Spartan typed in a message in the chat. I don't know if you saw it, Moshe. So he has left. I would have given him the word, but he appears to have left already. But he said, Moshe, a great historical overview, very inclusive. I want to add one more name to you, Dick de Bruin. He constructed one of the first theorem provers and wondered, as they become more complicated, how we can trust them. His answer, the provers may become complicated, but the proofs must be easily checkable by a small engine that can be proven correct.
Actually, that's a very good topic. And in fact, I wrote a column that's very much related to that. Can you save the chat, Hele?
Yes, I will try. And in any case, I can save.
And then you
this,
can send me the chat. Yeah.
Yes.
Well, thank you all. It was a wonderful discussion.
Thank you very much. And also thanks to our commentators for kicking off this, I think, very successful discussion. And we will then continue in a more informal setting in GatherTown. So we suggest that you all log out of Zoom so that you don't get any echo effects or similar. And if you've not used GatherTown before, the link is in the email you got, and it's very easy and intuitive. You have a little avatar that you can move around.
Sorry to interrupt, but the link is in the chat, right?
Yes. So there's indeed now a link in the chat for the GatherTown, and we hope to see you all there. And many of the VvL board members will also be present in case you would like to talk to us about VvL. So thanks again to everyone, and see you in GatherTown.